Okay, for our second example, we're looking at the acceleration of a particle at time t is given by r with two dots t equal to e to the t I plus 4e to the minus 2t j, where t is greater than or equal to 0. Sketch the path of the particle if r dot t equals I minus 2j and rt equals I plus 2j when t equals 0. Let's start by actually working through this problem and breaking it down a little bit more. So this first point here is acceleration. Now remember the two dots, that's my expression for acceleration. So let's not forget that's my acceleration right there. Okay, if we move on to the next part, sketch the path of the particle rt of I minus 2j. And I'm going to just show when t equals 0. This bit of information here, it's telling me that the initial velocity r dot of 0 is equal to I minus 2j. Okay, so we need to substitute in the 0 that's written over here to sort of make a little bit more sense of that expression. And then the next point that I'm given, let's change colours, let's use purple and purple. So my next point that I'm given here, that's r of t, again at t equals 0. So that point there is the initial position. So the initial position, no dot this time, the initial position when time is 0 is equal to I plus 2j. Alright, what do we need to actually do here? We need to sketch the path of the particle. So when we're asked to sketch the path, we are looking to create a simple x-y graph, and in order to do that, we're going to need the Cartesian equation. Alright, so we need to get the Cartesian equation. And before we can find the Cartesian equation, what we need to do is we need to get an expression for the path. Alright, so if we need to find the expression for a path, let's think about where I might actually start here. And let's go back to what we've been given. So we've been given the acceleration. So what I need to put together here is, if I start with the acceleration, if I anti-differentiate or find the integral, that would give me the velocity. Let's keep my colour scheme going here. That'll give me the velocity. And then if I anti-differentiate or find the integral of the velocity, then that's going to give me, sorry, I accidentally scrolled up there, that's going to give me the expression for the position. Okay. Now don't forget, when I find an integral, that's going to give me a constant of integration. So when we anti-differentiate, we always get that constant of integration. And the way we deal with that constant of integration is we've always had to substitute in a point to find out what that constant of integration is. The only difference in this problem to what we've done previously is that my initial points are vectors. And we're working with vectors, not just expressions that are x and y's. So let's have a look at what that looks like when we work through this problem. Let's start with, and I'm going to say acceleration, even though they've got the two dots on the r, I'm going to start with acceleration is e to the t I plus 4e to the minus 2t j. Alright, so what does that look like? When I find the integral of this expression, with respect to t, that'll give me an expression for the velocity. So anti-differentiate e to the t, you get e to the t. Anti-differentiate 4e to the minus 2t, well, I've got to take my constant that I had, divide by whatever the coefficient of the t value was, and then keep the power. And then we're going to have a plus c. Alright, so what does this give me? I'm just going to tidy that up a little bit before I go any further. That becomes minus 2e to the minus 2t j I plus c. Okay, we know that when t equals 0, that this expression has to equal that initial velocity. It has to equal I minus 2j. It has to equal I minus 2j. So e to the power of 0 is I. Minus 2e to the power of 0 is minus 2j plus c has to equal I minus 2j. And I can see from this expression the only way that they can be equivalent is if c is also equal to 0. So in this case, my c cancelled out. No c's. No extra values that need to be added in here. Alright, so now let's find the position. Let's find r of t. And r of t is going to come from the integral of the velocity. And our velocity is e to the t I minus 2e to the minus 2t j dt. Remember, because c was equal to 0. Anti-differentiate this, I get e to the t I. Now, anti-differentiate the next bit, I'd get e to the minus 2t j plus, again, some constant of integration. Now, I'm not going to call this one c because I've already used c. I'm going to call this c1, second c value. Alright, just like before, if we substitute in 0, I would get e to the 0 I plus e to the 0 j plus some constant of integration, and that has to equal I plus 2j. I plus 2j. Alright, let's tidy this up. We get I plus j, because e to the power of 0 is just 1, plus c1 has to equal I plus 2j. Now if we subtract vectors, in this case c is not going to be 0. I've got the I plus 2j, that's what was already on the right hand side, take away the I plus j, that's what's on the left hand side that we don't want. If we do this, the i's cancel out and we're left with just 1j. So we get c1 equals j, or 1j. Okay, so how does that look in my expression? My position vector now is e to the t I plus e to the minus 2t j plus my c value, which is 1j. Now I've deliberately left the 1 in there because I wouldn't normally leave it written like this. What I would do is I would write this as a single expression for j, a single expression for the j component. And the way I do that is just bring in some bring in some brackets, take out the j as a constant or as a common factor, and write my expression like that. Okay, so this is my rule for my position vector r of t, and we know that t is greater than or equal to 0. So let's consider my x components here. If x of t is equal to e of t, that's the I part, and I know t is greater than or equal to 0, then my x of t value, it has to be greater than or equal to 1. Now we've seen that in a few other examples, but really simply if this is t, this is x, and I sketch a graph of e to the t from 1 onwards, then this starting point is when t equals 0 and x equals 1. So that becomes the domain for the Cartesian equation. Okay, now let's look at the y part. So y of t is equal to e to the minus 2t plus 1. If t is greater than or equal to 0, let's again have a little squiz at my graph. Now if I've got e to the minus 2t, that would normally go like this. Wow, a bit wobbly there with my line, but that's alright. And then if I move the whole expression up one place, then I would have an asymptote at y equals 1. And this point, again, I don't need the expression on the left-hand side when t is less than 0. So that point, if I've moved it up one spot, will be at 2, 0. That's not correct. I've written my coordinate back to front there. So that point has to be when t is 0, y is 2. So y is going to be greater than or equal to that asymptote at 1, and not equal to, just greater than. And it's going to be less than or equal to 2. And then this becomes the range of my Cartesian equation. Cool, so we're starting to put together all of our components here. We've got a lot going on in this one simple question. So now we've actually got to work out my Cartesian equation. And the way I'm going to do that is I'm going to substitute this x value into the y expression. And I'm first going to do a little bit of manipulation on this y expression, and I'm going to write that e to the minus 2t. I'm going to separate that power into two parts so that I can substitute the x value in. And then that gives me y equals x to the power of negative 2 plus 1, where x is greater than or equal to 1. So x is greater than or equal to 1. So if I've got to sketch this path, let's have a little bit more of a think about what that graph looks like. It is a truncus, and it is a truncus that has shifted up one place. So a truncus will normally look like this. So my normal truncus goes like that. Okay, and it has an asymptote at y equals 0. So if I shift my graph up one place and I only go from x greater than 1, my final graph isn't going to look quite like that. It is going to move up one place. So that's my asymptote will go up one place, and it's only from when x equals 1. So if x equals 1 here, that's going to be at the point 2. And that makes sense because that's my y value of 2. So x equals 1, y equals 2. And then my graph from there is going to go down, but stay above that asymptote. And that is the path of my particle.